Okay, so I'm a little bit sick, so bear with me. So welcome to the Embodied AI panel. So before we start, I want to introduce our panelists. So myself, I'm Marc Pollefeys. I'm a professor at ETH Zurich in computer vision, AI, robotics related topics. And I'm also working at Microsoft, leading the spatial AI lab, also in Zurich. Then we have Marco Hutter next to me here. He's the director of the robotic system lab at ETH, and also senior director of research at the Boston Dynamics AI Institute, also in Zurich. Then we have Raquel Urtasun. She's the founder and CEO of Waabi, and also a professor of computer science at the University of Toronto. Previously also involved with Uber research in Toronto, and actually very long ago, a PhD student at APFL, the ETH sister university here in Switzerland. And then last but not least, Peter Fankhauser is co-founder and CEO of ANYbotics, and essentially has helped build this thing here and commercialize. And so this is Animal that is also going to be with us here, but he's promised to stay quiet. Okay. Okay, so this is a prime example, of course, of embodied AI, of having algorithms, AI algorithms, be able to drive physical systems. Nowadays, so since AI, of course, has had a lot of developments actually in the field, I would say there's been breakthroughs over the last over a decade and much longer. But let's say in our field of computer vision, for example, I think a lot of it goes back to around 2012 when data, GPUs, and algorithms came together and showed that learned systems could actually beat much more of the hand tweak system and more classical systems. And then, of course, for this was on the research, on the science side and the research side. In the last 2 years, of course, everybody's been familiar with ChatGPT coming through. Lots of excitement. The AI house started last year. Lots of excitement around AI, so this has now broke through to the broader public. And so, at some level, there's been this interest of seeing, well, if we have solved AI, we'll discuss that more during the panel. But if we have solved AI, there's of course, let's say this naive. So I'll start with that picture. There's this naive of, we solved AI, we can bring a lot of productivity gains for information workers. AI is mostly text-based systems, LLM, and things like that. So we can really boost the productivity of people working with information. Can we do the same in the physical world? Right. So that's the question. That's something that at every level, naively, you can very quickly kind of get a lot of excitement there. Right? And so I think that's why we're here. There's a lot of excitement in the space, a lot of funding going to companies that are building all kinds of things. Most excitement is probably around humanoid robots. Of course, with the idea, well, if we have AI, we can combine it with a body, then we can essentially have those robots do all kinds of things, for us, and it's going to bring a lot of value and a lot of productivity and so on. But of course, there's only one side of the picture. This is in many ways very naive. It's actually probably going to take a lot longer to get to have humanoids actually really carry out many tasks. However, I think there is today already a lot that is possible, and there are real-world applications, there are real-world deployments that are starting to come, to actually break through. And so, maybe there, I'd like to maybe first ask Marco to a little bit, discuss in terms of how he sees embodied AI and, from the side of the, let's say, the research side, but also the application side.
Sure. So I'm coming out of the field of mobile robotics, and I think that's the perfect example of what embodied AI is. I mean, you mentioned before, it's where the AI, which is a pure data processing part, meets physics and has something that operates in the real world. And I think what you have seen much earlier is that we had certain algorithms that were AI-based for processing image data, for other things, which downstreams are used using classic control methods. But over the last maybe 5-10 years, we have seen a tremendous change there, that essentially robots like this that we see here, they are controlled by a pure neural network. And that's kind of, for me, it's like the real embodied AI part. And I think that's something that has been integrated in the meanwhile on many different mobile systems, so humanoid robots, other legged systems, but also more classical robotic devices. And what it brings together is like having this multimodality of what we perceive from our world, what we see, LiDAR data, perception data, camera data, but also what we feel in our world, and then close the loop and have an action. So that to me is kind of the embodied AI aspect of what you're discussing here.
So maybe in terms of applications then, Raquel, maybe you can start and then we'll continue with Péter on the applications that you are particularly working on, and then maybe the other ones that you are.
Yeah, so at Waabi we are, think of it of revolutionizing the physical world by bringing next generation generative AI. And the idea is to really empower humans to have a more, sustainable future, right? So there is a human there in the loop where we should be doing better jobs. We should be, focusing our neurons into, more advanced things that many people today do. So we are starting with self-driving and in particular tracking because it's really ripe for this technology. And what is important to note is that, I believe that it's one of the first applications where you can really, you will really be able to see the scale. The reason why is that, the customers really need this technology. There is no way to convince humans to actually be long-haul truck drivers. This is a very hard job. There is 80,000 truck drivers missing just in the US alone, and these numbers are continuing to grow significantly. The conditions of that is actually pretty hard. So with generative AI, with this next generation technology, you can really, for the first time, build a scalable solution that you can really scale to multiple, geographies, and in a much more capital efficient manner, so that you finally have kind of the technology together with the use case and the customers together with, the scaling as well. So it's very exciting where we are today, where, we will be launching driverless by the end of the year. That means that in our Class 8, the biggest trucks that you can see in Texas, there will be no human driving on board. So it will be all purely driven by our robots, which are, much safer than humans. So it's a very exciting time, and the era of physical AI is really starting now, and the world is about to change.
So at ANYbotics, our vision is to create a workforce of autonomous robots, because we're convinced that in the future, companies will not only hire people, they will hire robots who get the job done. And that's certainly for the reason that often in industrial facilities where we work, there's not enough people to go around who can and want to do those jobs. The entire demographics, there's more people above 50 who do maintenance and repair and inspection jobs than younger people. Often in hazardous environments, so safety is a big challenge. And also today we're using a lot the eyes and the ears of people to collect data. And people are not meant, right, to collect all that data. We rather focus them on creative tasks, decision making. So what we're building, our first product, is Animal, a four-legged robot that walks in industrial facilities. It takes pictures, analyzes pictures, thermography, acoustics, 3D measurements, all of that. So it's about bringing the data reliably and frequently back to these operators and to data management systems to run facilities at a much higher productivity and safety. AI for us has been a game changer. As you can imagine, these facilities are built for humans. So they're extremely complex, stacked on top of each other, stairs, steps. There's people moving around, things change constantly, right? So we're bringing here a robot into a very dynamic world, also external influences, rain, snow, all of that. And so in a traditional sense, programming a robot would be extremely difficult, nearly impossible probably. So with AI, we've been applying deep reinforcement learning on our robots for the last 5 years. We soon shipped around 200 of these systems that are completely driven by AI, self-learned. And the results are really staggering, right? The robots can extremely reliably, at 99.8% success rate, climb stairs, steps, and move safely through facilities, and do that fully autonomously. It's all on-board processing, LiDAR, step sensors. In an environment, there's also no cloud connectivity, right? So for us, embodied AI and then embedded AI, meaning you run it on the system, taking the sensors in real time, and then executing on it.
Maybe actually following on some of that with Raquel. So I remember you wrote in 2012, you wrote a paper, are we ready for autonomous driving, right? So we weren't, right? But what changed? If you summarize over that decade.
And I guess a paper very dear to my heart, and at the time was about, there was not even a way to evaluate whether we are ready versus not, right? So we kind of created the first big public benchmark to really empower academia as well as industry to do research and to be able to understand, what methods work versus not. And there was a lot of, many, thousands of groups really working on this. And it was interesting to see. Even today, it's still, alive, Kitty, the data set, which is mind-blowing to me.
I think, by the way, by now it's a little bit expired. It's actually hurting a little bit because it's too narrow. But
it was 2010 when we started.
Oh, exactly,
so
exactly.
In academia, this is what we could do. So what we've seen is obviously we were absolutely not ready at the time, we've seen now a big shift in terms of technology, right? So there is what we call AV 1.0, which were these very highly engineered systems where you need a lot of humans to actually be kind of programming small modules in a very, very complex software stack where there is AI in some of these models, but at the end of the day, there is an overarching system that is very, hand-tuned, hand-engineered, where you need, thousands of people. You need to go on the road, drive, millions of miles to chase your next set of corner cases and add more models to the spaghetti stack that I call, right? So this is brute force by humans. We see over the last couple of years that there's a shift towards AV 2.0, which is the idea of a single end-to-end system that is able to do all the tasks necessary for driving. Right? A canonical example will be Tesla, where for level 2 systems, which is where you still have the human that can actually intervene, and camera only, there has been deployments in the US, across the world as well as China, for this kind of technology. Now, when you think of level 4, which is you're going to remove the human from the loop, the level of difficulty changes dramatically. So it's not that, I have a level 2 system that is great, and I'm going to get to level 4, from one day to the next. So the safety considerations are massive. So then what we are seeing, and the reason I started Waabi 3.5 years ago is I saw a tremendous opportunity to really disturb the market by bringing next generation of, say, AV 2.0, where the idea is that can you build systems that can really abstract and understand and use reasoning in order to understand what are all the options of the things that they can do, the consequences of those, the actions that they can do, and then at every point in time choose the right decision. And that has been mind-blowing in terms of the abilities of the system to handle things that I have never seen before. I've been in self-driving for over 15 years today, and it's amazing. Every day I'm amazed by the power of this technology. And the second bit that was very important as well in the shift is that, well, now that everything is shifting to AI, then data becomes almost more important than the algorithms, right? And the question is, well, do I need millions of vehicles or billions of vehicles driving around in order to be able to deploy? Well, no, if you're able to actually create a simulator that is as good as the real world, and you can prove that actually is the same as the real world. So that's the second kind of core piece of technology that we built that has enabled us to go so fast and be on the verge of launching driverless with a fraction of the capital. And just for context, nobody has been able to launch a self-driving truck on public roads today without a human. So that's kind of like the evolution of the technology, and then we will see more and more of these systems that are able to reason across many different use cases, not just self-driving.
But still somewhere, how much do you need to, if you model the world, like how much can you bring in all of the, often long tail unforeseen elements? Partially, if you didn't put them in at some point, they might, so how can you close that gap essentially?
Yeah. So this is where simulation is a must, right? Where the way that our simulator works is that we can automatically clone the world, and everything that you have seen once can actually be recreated doing all sorts of different things. For example, Marc, if I see you once, I can create you doing all sorts of different things, no matter where in the world. So it's a very scalable solution, and that's the way that you can actually then, at the scale, simulate all the possible interactions and things, weather conditions, etc. With, as I said, a level of realism which is unprecedented. Actually, we can show that for the machine there is no difference between reality and the simulator, which is something that we haven't seen in any simulator out there. Now, the other thing that is very, very exciting is that since now we are talking about neural simulators, they are an independent AI system. So now you have these two AI systems that can play a game, which is the simulator is the adversary, and the other AI system is the student that is trying to learn, right? The virtual driver that drives the self-driving vehicles. So now the simulator can actually create the examples that are the corner cases for that particular virtual driver. And that's the way that you can actually be super efficient in terms of testing and creating examples that enable you to learn really, really fast. But without simulation, it's impossible to think about all these corner cases, etc.
As a complement to that, on these type of robots and so on, a big element has been the reinforcement learning, I think. How do you see those things coming together? What are the touching points? What is the kind of the AI stack for embodied systems down the road?
So if you're looking at an autonomous truck, the controls problem itself, the local controls problem is relatively simple if you compare that to, let's say, dexterous manipulation or a humanoid that does a very complex interaction tasks. And I think that's where the RL component has made a huge difference. And similar as Raquel said before, also there the whole data generation through synthetic data generation, simulation has been like a game changer. I think right now we do have sufficiently good, sufficiently precise, and sufficiently diverse simulation data available that the trained control policies that are running on these robots, they are just significantly more robust than anything that has kind of a classic way in how you try to model uncertainties or the world around you. And the bridge from this to make it essentially a capable system is happening through whatever happens now in these big foundation models, the large language models and vision models, which help us to hopefully embed some sort of a common sense into these robotic systems, that the way how we understand and write down about the world and have the connections between things, that this type of connection can be embedded in robotic platforms, that we leave the times where we have to handcraft state machines and identify these corner cases and then find a new way how we get around these corner cases, but that these things are evolving much more from like how we interpret, how we see the world, from huge amount of video data and text data, and bridging that together with, in that case, walking robots or mobile manipulators or humanoids.
But then still, if we look at, and then this is maybe for Raquel, like the importance, but also for all of you, the importance of sensors. So, Tesla has been, pushing, redefining like things along the way. I remember their 2021 event where Andrej Karpathy was, showing how they would kind of solve some of the problems. Showed, for example, a car with a bike rack behind it. That had been a problem, of course, because the Tesla, the first time around, it's our bike rack. It thought a bike was crossing the street. It hit the brakes, big risk. So they picked that element, and then they said, okay, this is a problem. Let's feed it back into our system. We're going to train on this, learn to ignore this, or learn to handle it appropriately. But that's, of course, a one by one kind of eating through the long tail of problems. I think so. I don't think we've seen camera-only systems being able to reach a level of safety and security that is actually deployable, right? So they're still officially level 2. But of course, Waymo, with a much bigger stack of sensors, I think it's a big part. It's seeing if the world, at least the interpretation of the world, is self-consistent in a sense. It's much easier if you have 4 or 5 ways to look at the world. So how do you look at that?
Yeah, great question, Marc. And maybe I will start with going back to my academic days, where I used to say that, this existence proof of a system that can actually drive with even 1 or 2 cameras, which is humans, and therefore we can do it as well with machines. Now, as an entrepreneur, it's a very different story, which is not about solving the hardest problems in the world. It's about how we can actually build a product that is really, really safe, because there is many lives that are waiting for us to save with this technology, right? So in the context of level 4, using an heterogeneous set of sensors, LiDAR, cameras, radar, use also sound with microphones, because emergency vehicles, sometimes you don't see them, but you hear them, right? So using a redundant set of sensors that are very complementary is tremendously important for safety. And maybe in the future, in a very, very long future, a camera-only system might actually, or with some, might get us there, but that will be a much more difficult path in order to really build a safe system. So very different how I feel today than how I feel at the time, and it increases the BOM cost of of the robots, but you shouldn't compromise safety, and that's very, very important. Now, from the technology side, what is interesting with our foundation models is that they are multimodal to the next level, right? Radar, LiDAR, cameras, sound, they have to understand all these different things, and many of these sensors place and working at different frame rates, not necessarily synchronized, etc. So there is some very, very interesting, I would say, research questions and challenges along the way that, with some really exciting innovations that we have done in order to be able to push the technology to be able to do that.
What about maps? I've heard some people say that maps are also, in a sense, they count it as a sensor.
So I will be one of those. So and there is confusion today by some narrative that some people are trying to do, where end-to-end systems and maps, they are not incompatible. Okay, an end-to-end system is just an AI system that takes sensors, where the map for me is an additional sensor, right? And then needs to do all the tasks necessary for driving. So at Waabi, again, safety first. So we build our own high-definition maps. And traditionally, high-definition maps have been very unscalable, very expensive to build. Typically $1,000 to $2,000, per mile. Of those maps, right? So if you multiply by how many roads you have in the world, the math is pretty staggering, right? So with the technology that we have built, it costs us less than $50 per mile to have super precise high definition maps. And it's all thanks to, again, generative AI that automates almost everything in the process. And then we just have a final human QA, and that all the semantics, all the stuff are correct. So that's the way that you can really scale the technology. And then why do I call it sensor? It's very important because the sensors as well as the maps might be wrong, right? The sensors might be noisy. Maybe in Texas where we drive today, we have our commercial operations, there is massive bugs, right? That can actually, get on the way of your sensor sometimes, and this is why automatic cleaning is very important and whatnot, but it can corrupt the sensor. The maps also might be not up to date, maybe there is construction, etc. So there is also an online mapping component that runs real time at every point in time on the vehicle. So that's the way that you get the best of both worlds. You get kind of the next layers of safety while utilizing that information, and it's very useful when it's right.
Péter, in terms of sensors, for platforms like this or platforms that move about kind of more human scale kind of environments, what is important there?
We follow the same approach. Safety and reliability is first, right? Reliability for robots is the holy grail to achieve that. Our customers are very conservative. Safety first, right? If you think oil and gas chemicals facilities, there's no room for error. So we take the best stats on the market. What we have currently is 6 depth cameras, right? So 6 times a pair of eyes, including infrared lighting to see the train as good as possible. In the back, you see a LiDAR, hundreds of thousands of points scanning the entire room in real time. And then you need to compute to process all of that. So for us, in the first phase, it's all about what is the best sensors you get. For us, it's time to value, right? So how quickly can we build these machines? That's the most important part. In the long term, I'm very excited about also then lowering cost of the system. So over time, you will see you can use cheaper sensors. And what we've already seen is that we don't need sensors everywhere. So for example, we don't have sensing in the feet. Some of the robots might have flexible legs, etc. And with AI, you can start compensating for a lack of components or even cheaper components, right? Certain backlash, less precision in manufacturing, etc. And this opens the door essentially for AI to eat into the cost of hardware, right? And this will then open up new applications where today a more expensive robot wouldn't have a sufficient ROI, but over time it becomes feasible to deploy these systems even in new applications.
Marco, so today this system and other systems also, Raquel's system is mostly about navigating the environment, right? Moving things around. The next challenge is being able to also manipulate the environment, do things in the environment. I think we actually have in front there someone from, I guess it's Mimic, right? There's a hand there. Maybe you can lift it so that everybody sees it. So there are huge challenges. So you said like with reinforcement learning, we are now ready to kind of do everything, right? And I think that's true for navigation. But what are the extra challenges that you see on the navigation, on the manipulation side, and with hands, both on the hardware and the software side?
I mean, that's exactly a good point, right? So the manipulation challenge starts with having the right hardware, and we don't have yet the right hardware. We have some hardware that does something and is good for certain things, but we are never at the level of what we have as a dexterous element. The actuation, the tactility, being able to sense something, being able to adapt to all of that, and also being able to cure ourselves to some extent. So all of that is like still far away. And if you're looking at this machine there, it's actually very, very simple, right? So you have one rubber foot and that's it, and that does its job. And if you look at the humanoids today, it's also very simple. They may have a little bit of flexibility in their foot, but that's it. So I think that we have huge challenges and we can improve a lot in getting that. If you're looking at manipulation itself, I think a lot of these technologies that have been developed more for locomotion and for controls, they more or less directly transfer to this. If you can describe what the system is supposed to be doing. Now the question is like, how do you describe all of that? Because there's a huge level of complexity that many of the tasks that you want to achieve or want the robots to achieve are in your environment. And that's where a lot of this imitation stream is coming in. Because the beauty is, we humans, we do many things. And you can go and you can start teaching how these things are done instead of having somebody who has to describe that and figure out how the right cost functions for this reward are. And that's where probably also this whole humanoid domain gets a huge boost because it's a similar morphology than we are. So things should be done in a similar way than what humans are doing, and hence imitating or doing the same way as what humans are doing is a feasible way to move forward.
So, what is your timeline on humanoids, let's say? And what are still the biggest gaps in it?
With all these things, right, it's always a question of like, for what? The answer to autonomous driving, whether it was possible not 10 years ago, was also yes, from an academic standpoint of view, right? It's all these problems like, can you make it safe enough that it is applicable? And if you want to have a humanoid that does a dance on stage, then it's ready today, we can do it. But if you have something at home doing elderly care and being potential danger to people and interacting with people, it's a very different story, right? I think we have to abstract there. And we also, and that's important for all the companies that are doing these businesses, is like figuring out what is the subset of things that we can do, which is also creating commercial value for somebody who's actually using this technology. And I think that's where Péter did a great move, right? This thing is doing something we know it can do today. There's lots of more things it can do in the future, but it's already beneficial today. And with the humanoid, I think we have to also find this balance. Right now, there's a big of a hype that like we're capable of doing everything in very short time. It will take a little longer, but we will find steps on the way that these things are becoming commercially feasible.
What is your prediction for the first, application in that humanoid robots will be able to to do beyond dancing on stage, like useful, productive application?
It's always hard to give predictions about this, right? If you're looking in a POC setup in what the big companies in automotive are doing today, where a robot comes, picks an object, put it somewhere else, without very complex interaction tasks, then we're talking about short time horizons. It's not something that will take another 5 to 10 years. But if you want to have a companion or something that is really helpful in doing a human level task execution of a more complex dexterous task, then we're talking at least 10 years.
So, Peter, so you're selling your robots across the world. What are still the challenges to deploy them more broadly or so? So you can already do lots of things. What are kind of the next things that you are trying to solve to open up a much broader set of applications?
So from a technical side, embodied AI, or if we talk about that, what are the challenges? Certainly there's a lot of talk about foundation models, the more data, etc., but we need to run this in real time on a robot. There's no connectivity often, right? It needs to work in 40, 50 degrees Celsius, so cooling becomes a problem. So ultimately, you're also restricted by that. However, with new sensors and then GPUs we're building in, the next steps are contextual understanding for the robot. The robot right now is still stupid. It sees the world as geometry. It's safe to be used, but it doesn't know, how is a human moving? What is this box if I interact with it? So contextual understanding will open up several things. Number one, it will be even safer to interact with it. So we'll be able to interact with people, certain distance keeping, etc. It will be able to understand the world, and you don't need to set it up again, yourself. Today we commission the robots with an engineer. Imagine in the future, you open a box, the robot comes out and knows its context, runs through the facility and comes back and says, look, these are the 100 things I've seen. These are 10 I can improve. Will be possible because the fleet has seen, thousands of facilities. And last, it's also human and robot interaction. Right now, we have a user interface, but imagine it can understand your gestures, speech, etc. This will be quite soon possible. Democratizing the use of robotics, right? It's not only about robotics engineers, but it will be as simple to use as ChatGPT.
So, Raquel, in terms of how do you, in the end, how do you prove safety of systems? So you're deploying. When I looked at it, and when I had personally to choose between, I decided to work back then on augmented reality as opposed to self-driving, where I felt it was a lot safer in terms of the kinetic energy involved. Essentially, now you went for massive amounts of kinetic energy in play. So how do you end up really proving that something is safe?
And just for context, right? So imagine the biggest truck, classic truck, with 80,000 pounds. So definitely the kinetic energy is pretty high there. I love these robots; they're amazing. Once you experience them, it's so no way back.
In metric, that's about 40 tons, right?
Yes. So, I guess I'm too North American by now. I'm European, I guess, by birth. So maybe also worth, before I go into exactly the safety piece, which is, what are, the really 3 challenges of bringing this technology to market. And I want to talk about this because, maybe there is a thought out there that, you take an LLM, the latest, greatest, you fine-tune it for the task of driving, and suddenly you have, the one-person company with, $1 billion and whatnot. So it's pretty far from that, where when you actually build a real physical system, which is that, there is 3 things that you need to do, right? One is build a system that can really generalize, right? And that's complicated. If you look at LLMs today, they do a lot of memorization, right? And for us, it has to work all the time, regardless of whether it's in the data versus not, right? So that's actually a challenge, and we will talk about the relationship with safety in a second. The second one you alluded to is about the efficiency. Right? You need to be very efficient in the deployment in the robot, but also in the way that you train those robots. Right? For this very complex task like driving, it's not that you can just do pure RL. That's going to take you forever, and you're going to burn billions of dollars to get to that point. So you need to build really intelligent algorithms and really intelligent architectures that generalize really well. And the last bit is that being safe is not enough, and that's kind of a paradox, but you need to be able to prove that it's safe enough so that you can actually put your safety case before deployment. Right? In the digital world, you put your product and then you try to patch in terms of maybe use cases and things that are less safe. In the physical world, you can't do that. Right? So you need to kind of prove it before you actually deploy it. As you think of, how do I prove that my truck is safer than a human? Well, if you look at the statistics of humans, in highways, for example, the rate of events is very, very low. It's a good thing, right? But it makes proving safety a harder problem than in cities. Let me give you some numbers just to ground this. Every 150,000 miles, there is property damage. Every 1 million miles or so, there is an accident with a small body injury. Life-threatening, every 10 million miles. Death on the road, this is humans, okay? Every 100 million miles. Now, you're right, you need to drive 100 million miles to see one of those incidents. Then the question is, how do I prove the safety of my system? How many miles do I need to drive? And to be statistically significant as scientists, that's what we want to do, right? Is now you are in the billions. Well, there is no way that people have the fleets to actually prove that, and you don't want to create accidents to prove this in the first place, right? So there is this really, really complex, proving safety in the case of particularly highway driving. So that's where simulation is a must. It's not that you have a choice, right? And people in the industry talk about simulation these days quite a bit, right? But it's about, I run, billions of simulations, but that doesn't really matter. What matters is, do you have coverage of all the things that you're going to see? And is the simulator really realistic? If you cannot show me that the system behaves the same in the real world and in simulation, doesn't matter how many simulations you run, because it has nothing to do with the real world, right? Otherwise, you're going to see problems in the real world that you don't see in simulation. And that's very, very dangerous. So that's something where, from day one, we invested in. We need to really solve the simulation problem. And that will be the enabler of the training the system, but more importantly, of making the safety case. And that's, in the way that we build Waabi well, right, is very exciting to see now that we can, clone and replicate everything that we see in the real world in simulation. And then you can really see that the system, the same software, the entire system will have done the same thing. And that's, a huge enabler of this safety case. And I call this safety 2.0 because that's where the industry should be going, which is the next level of safety. The traditional kind of VMV is not sufficient. We follow all the standards, but you can't prove safety just by doing traditional approaches to safety.
How do you get to coverage? So you said you can kind of mimic everything that's in the real world or so, but that means you have had to kind of drive those miles to get.
Yeah. Fantastic question. So coverage is a more tricky question, unless you have, and I haven't talked publicly about how we do coverage and whatnot. So this is maybe where the academic in me wants to talk, and then the CEO doesn't want to talk.
Okay, so let's let's switch to Péter then.
Thank you, Marc. You won.
Safety is a lot about the context and the environment. So that is also the reason why we have not started doing last mile delivery. Could be one of the applications, but on the street, you have, kids running around, dogs. There's so many things that move, and you have to assume somebody puts their finger into the robot, jumps in front of it, and also provokes the system until it fails, right? So starting at the industrial environments, these are highly controlled and environments where you have trained people, closed shoes, just the basics, right? And so part of us of achieving, for the last 5 years, deploying robots was that part of the safety is also offloaded to the user. So all of them get training. There's a clear manual how to use the systems, not to put your fingers there, to stand clear of the stairs when the robot is there. And what we do from our side is following the machine directive, right? Right now, there's a lot of talk about AI safety. For us, this will be relevant. It's becoming relevant, but there's basics, EMC, lab testing, right? E-stop button, certified electronics. These are standard systems that are known from the traditional machine industry that you can apply on such a robot as well. And with that combination, we were fully able to CE, FCC certify these robots. We have a robot now that is able to go into explosive atmosphere, so we not create a spark. So really following here the needs of the industry and the requests when building these machines.
Okay. Anything you want to add, Marco, about those topics?
Maybe one thing to add on the discussion of the sensor, and that's also more from an academic point of view. I think downscaling sensors is great from reducing cost perspective, but I think we have to upscale it. We want to have superhuman capabilities with these robots. That's what and that's a unique opportunity we have right now with these robots. On one side, we give it more information. But the other side also that for the first time, we also have machines in the real world experiencing what is the consequence of the action. And I think that allows us to close these loops and to actively generate this data and to make the systems a lot better in the future.
Yeah, I would say maybe, Marc, that these machines see much more than humans, right? Humans, we have a field of view, there is a cut in order to modify this, etc. They see 360 and they pay attention to everything all the time. the good thing about sensors is that economies at a scale work really, really well once you are to those volumes. So it's not necessary that you really need to reduce the sensors. They are already, you know, I mean, depends on which player you're talking about. Some of them are really overly, you know, they use way too many. But you know, in the tracking, maybe worth mentioning, in the tracking space, you know, one of these regular trucks, not self-driving, is already like $200,000, right? So you can afford actually cost of sensors that is very different from a passenger car that is, you know, $10,000, $15,000, right? So that's you know, one of the things that we don't need to compromise so much on the BOM cost, and you can recoup that cost in less than a year.
Okay, so I think it's with about 15 minutes left, I think it's a good time to open up for questions from the audience. So I'll start over there in the back.
Yeah, I can speak up. So yeah, thanks for the discussion. And I'm Waabi, and I'm from Zurich. So I work with Professor Urtasun and Luca Benini. So I work on building efficient AI systems with software and hardware approach. Actually, I also had a collaboration with Marc, if you remember me.
You have to say yes now.
So my question is, it is said that the year of 2025 is a year of agentic or embodied AI. So I want to know what your projection of the breakthrough in 2025. And another question is, what do you think of the interaction between agentic AI and physical AI?
Okay, maybe I can start and then you guys can follow. I think agentic AI is much broader. I think we'll see a lot happening in agentic AI, but in the digital space, where it's much easier, much more controlled, in some ways safer, although you know there's obviously also questions there. But so that's kind of that's something that there's a lot going on there, and so being able to ask your computer to carry out a simple task and this and that, those are things that we'll see. Probably in the coming year and so on, or already seeing or so. I think it's of course very much, connected to embodied AI, because that's obviously what you want to be able to do also, and ask, your robots to carry out a task. So robots are obviously essentially agents, physical agents that can carry out tasks. You can ask, a truck to move something from here to there, or things like that. So I think it's very connected. But I think we'll see much more happening actually in the digital space, in that space, than before we see it happening in the physical space. Or at least we'll see it happening in the physical space at a much smaller scale. Anybody else?
If you have an autonomous truck by end of the year, I think this is already a great thing.
Yeah, I would say that, as I was alluding to before, foundational models that can reason is kind of the equivalent of agentic AI in the embodied AI space. And then the role of simulation, where agentic AI-like things you might see on those simulators. So there is some connections, but there is some differences as well.
Okay. Yeah.
Hi, Women in AI Governance. I wanted to understand a little bit more from the scalability and the bias and the cloning. How do you account for human behavior cloning? So, for example, your truck's very exciting, but you come from Switzerland. If you cross the Ticino end of the border, you start driving in Italy with the kind of same safety rules. That truck would kind of come to a standstill with Italian driving, for example. So how are you equating to make it, so everyone knows what I mean, how do you equate the scalability when you have different cultural norms on the road and the way humans interact?
Yeah. So maybe to clarify, like, we don't need to clone to be able to simulate behavior, right? We learn, so as part of the simulator, which is modular, there is behavioral models that are, and we use a plethora of behavioral models. The reason why is that you don't want to overfit to this type of human in the world or animal or whatever, right? You want to be able to say, no matter how they behave, the system is still safe. As it relates to moving geographies and the fact that folks behave very differently, you might need to tune a little bit your behavioral models, for example, on the simulator, right? As an example, Southeast Asia people drive very, very differently than in Europe and North America. Even much more different than Italians versus not, if you gotta get to that. So that requires definitely, a bit more, training and some data, etc. So it's a bit of tuning, but you don't need to hardcore any rules. With a little bit of data, we are able to, handle different, different behaviors that would be more, even within a single country, you see very different behaviors. The other thing that I want to touch upon is you mentioned also bias in your sentence, which is a very different question. And that's where I think that, again, simulation is a must. Why is this? Is if you typically see the deployment of these vehicles, they might be in certain neighborhoods, and maybe certain population groups that actually live there, so the data might be biased towards, and then if you train models with that, they might actually be better and be biased with respect to some populations, right? And you can construct always to have a subgroup that may be some bias. So that's where, with simulation, you're able to create the same scenarios by changing who the population is, etc., so that these systems are not biased. So it's really an incredible tool that to me solves many problems. But there is obviously a lot of challenges into building such a system. But fantastic question.
Okay, so I see lots of hands. I'll start in the back there.
Mister, I'm so sorry.
Hello. Yes, thank you very much for the panel. Super insightful. I'm Joel de la Fuente. I'm leading the VR/AR Association in Switzerland. And yes, so I have a question for you, Raquel. I'm also Spanish, and actually I was watching the CES keynote from NVIDIA earlier this month, where some updates were announced, such as, for example, Cosmos technology, as well as some partnerships with companies like Toyota. I know that NVIDIA is one of your investors in the Series B, and I'm curious to get your perspective on what does that entail for the autonomous driving industry, and how do you think this could have an impact in the upcoming year?
Yeah, and Jensen Juan, amazing CEO and person. So definitely somebody to follow, and I would say a mentor for me, since I know him over the last 10 years. So if you follow that, one of the things that Jensen says that is really the year of physical AI, right? And we're gonna see this across many form factors, right? And he highlighted our trucks on stage as well, which is we have a very exciting partnership with NVIDIA that is multifolded. On one side, we announced last year we're building the Gen AI compute for embedded AI for the trucks. So that's a very exciting partnership, of how you build something that consumes very little power, and you can actually drive, with these models. The second partnership, so the investment right there, big investors of Waabi, and the third piece will be, we announced a partnership with Cosmos. And the way that we see Cosmos is, so we have our proprietary foundation models, we have our proprietary simulation, but the ecosystem of Cosmos can potentially really accelerate even further our development while still being proprietary. And that's a very exciting collaboration with the NVIDIA team, and many more things that you might see.
As Italians, I grew up. Please use the mic for live stream. Thank you. Hi, thank you. As Italians, I should say something about the way we drive, but I don't go on this path. It will take us too far. My question is related to my job. I work for an insurance company, which is the leading insurance company in Italy for motors. We also leader in telematics on board. So we install telematics and collect data from traffic for 4.5 millions of vehicles. And we analyze data, and we are also looking at the autonomous vehicle perspective. My question is, how did you solve the insurance problem with autonomous drive? So who's the fault for accident? Is it the fault for the algorithm, for yourself, or?
Yeah, so there is the liability kind of problem, if you want to call it problem. And then there is the kind of insurance of self-driving and how that's going to look like. So in terms of in the tracking ecosystem, so the liability is shared, and there is 3 players really. There is the OEM provides the base platform that is not a regular truck, it's a redundant truck built explicitly for self-driving. That's why an OEM partnership is very, very important. So they are liable sort of like for that in general. I'm talking here not necessarily about partnerships, okay? So they are in general liable for if something goes bad in the platform itself. Then you have the AV provider that provide, sort of like some hardware components, as well as the virtual driver that drives the vehicle. If something goes bad on the virtual driver and makes the wrong decision, etc., liability relies more on that. The third piece is that on the trucking side, then you have the operators. We sell the trucks, right, together with the OEM, go to market to the carriers, the private fleets. They are responsible for making enhanced inspections, making sure that there's certain things in the way that you operate these trucks that you should follow. Otherwise, there is liability on that side as well. So it's a complex ecosystem of liability. But hopefully you get a sense of that piece. As it relates to insurance, it's very, very, very interesting, and the biggest insurers are very interested into getting into the self-driving world. And in all transparency, there is still a lot to figure out in terms of how that will play. But at the same time, what we see is that in small volumes, insurance is probably higher, right, than regular humans. But as the volumes increase, as the safety numbers come, and you actually can really see how that is much safer than humans, then and the fact that there is less nuclear vertex because everything is recorded, so you can really, if somebody sues you, you can actually inspect whether it's true versus not. Then those insurance costs are gonna, dramatically reduce. That's how we see it, and that actually gets some extra savings for the customers as well. So we will go through a period, but it's a very, very interesting conversation that we're having now with, the who is who in insurance today.
Okay, so I think there was a question in the back there.
Thank you very much. Thank you for this wide-ranging conversation. I'm Turaj. I'm with Serve Robotics, the company behind the cute delivery robots, last-mile robots that you may have seen at the Uber Pavilion here. If not, check it out. So the question here, at the risk of even widening the conversation even more, physical world has also regulations, right? So I would love for you to talk a little bit about how do you also plan to navigate not just the physical world, but the regulatory world? Because especially with Waabi, as you're going through multiple states, each having their own regulations, what's your strategy and how do you deal with that?
You guys want to start first?
I can start quickly. And also giving a hint at the panel session that we have later on safe AI and regulations. For us, luckily, these industries are heavily regulated. There's ISO standards, etc., right? So we find few local discrepancies, but mostly cultural differences. Meaning that if we adhere to the US, European, Asia-Pacific regulations, and we design the systems from the beginning with in mind, we can scale extremely well. Now, there's a lot of the machine directive that determines a lot on the basic physical safety and electronics, but in these, there's new regulations coming up, the European AI Act, etc., that plays a role. It's not fully understood yet what it means. What we can do is contribute, show how these systems work. There's a lot of also misunderstandings there, so we're actively participating and shaping the landscape. Less for favoritism for us, but more that we can evolve and make robotics and all these fantastic opportunities accessible by everybody.
Yeah, if I can add on the self-driving side, so we have great policy, public affairs teams that work very, very closely with the regulators in multiple facets, including the fact that so for them to really understand what the technology is, can do, etc. So the partnership with regulators is, I would say, tremendously important for this industry as it's evolving. Now, in the US, we can actually launch driverless in more than 30 states. So it's state by state, it's not federal, but it's a very, very kind of open policy. And that's, apart from the massive freight market, that's one of the reasons why you see ground zero for self-driving trucking in the US today, and Texas being kind of like where everybody is and launching first, no surprises there. As it relates to, for example, Europe, regulation is one of the things that are going to prevent, or are going to, not prevent, but slow down the adoption of this technology in Europe. and that's unfortunate, but we see kind of this deployment being more like 3 to 5 years out compared to the States being now. So we will see how things evolve. With Canada, we are working very closely with the provinces in order to enable also a regulatory framework that enables the safe test and then potentially deployment later on. But there is still a lot to do. So definitely the US is ahead in terms of regulatory, and as that deployment happens, as the number comes in terms of safety numbers, I think regulations will be kind of change across other countries as well.
Okay, I know there's many more questions, but we're running out of time. So I want to thank my co-panelists and all of you for attending and for the great questions. And I think we'll stop it here then.